Hello and welcome to our presentation. In this presentation, we will talk about the Mars atmosphere and volatile evolution, or MAVEN. The overview for this mission. The MAVEN mission is a part of NASA's Mars Cult program, in which it collects data from the Mars ionosphere and outer atmosphere. It was launched in November 2013 and it was funded by the NASA HQ. The data would then be used to determine the role that loss of volatiles from the Mars atmosphere to space has played through time, giving insight into the history of Mars atmosphere and climate, liquid water, and planetary habitability. The project is led by Dr. Bruce Jakosky of the University of Colorado. The launching site is the Cape Canaveral Air Force Station Space Launch Complex 41, designated for Atlas V version 401. The latitude of this launch complex is 28.583333 degrees north and 80.583056 degrees west. The advantages of this launching site is the sparsely populated downrange area, which is the Atlantic Ocean, so it can cause minimal damage when any part of the mission drops, and it has the ability to take advantage of the Earth rotation, as it is the nearest American space launch complex to the equator. The launch vehicle is the Atlas V version 401. You can see the specification here, and it has 2 stages, and you can see the specification for a stage here.
Okay, so this is our reconstruction of the mission, but this is the additional data. This is the inclination of the rocket's trajectory, and we can find the azimuth by using this using this equation. Cosinus of the inclination is equals to cos of latitude times sinus of beta. Beta is the azimuth, and we get that the beta is 94 degree. We know that the Mars radius is 3,389.5 kilometers. Earth is 6,371 kilometers, and distance from Earth to Sun is 149.6 times 10 to the power of 6 kilometers. Sorry, and the distance from Mars to Sun is 227.9 times 10 to the power of 6 kilometers. We also found the satellite's mass, the mission's satellite mass. It's actually 2,454 kilograms. And for the orbit, we assume that the planet's orbit is circular also, and the parking orbit is circular. So we use the furthest point from the Earth for the parking orbit, from the actual parking orbit. So the R is 6,686 kilometers. We can find the velocity at the parking orbit by using Christopher integral equation, and we get that the velocity at the parking orbit is 7.72 kilometer per second. And we also assume that the theta of the Earth is 300 degree, and this is the actual mission transfer orbit trajectory. It's not actually 300, but we just assume to ease our calculation, sorry. And we can find the the eccentricity of the transfer orbit by using this equation. We get that the eccentricity is 0.259. We also can find the semi-major axis of the orbit, the transfer orbit. By using this equation, we get 1.81 times 10 to the power of 8 kilometers, and we can also get the orbit pericenter, which is equals to 1.341 times 10 to the power of 8. We can use the semi-major axis and the pericenter radius to find the delta V and we assume that the delta V is equals to V infinite to escape the Earth orbit, and we get that by subtracting the V of the satellite at Earth by velocity of the Earth. We get those velocities by using physical integrals, and we get the velocities is these velocities, and we get the V infinite is 2.443 kilometers per second. From that, we can find the same major axis of the hyperbolic escape trajectory, which is minus 6.679 times 10 to the power of 4 kilometers, and we can find the E also by using this equation. The E is 1.1001, and we can find the delta V by subtracting V of pericenter of the hyperbolic subtracted by velocity as circular. We get that the delta V is 3.469 kilometers per second, and actually we can find the fuel needed by using this equation. We get the fuel is 2452.0745 kilograms. For the arrival, we first needed to find the V arrival by using the visual integral equation. We get it by using the R of Mars and A of the transfer orbit, and we get the V arrival as 20.77 kilometers per second, and we can find the V of Mars too by using physical integral equation, and we get it as 24.13 kilometers per second. And so we assume the gamma of the satellite is 5 degrees, and we assume that the velocity vector of Mars is downwards, like straightly downwards, and we can find the V infinite by using the cosinus equation, and we get it as 3.886 kilometers per second. After that, we can find the A by using physical integral equation, and we get it as 2.836 times 10 to the power of 3 kilometers, and phi at hyperbolic pericenter of arrival is 6.15 kilometers per second. We can also find the E by using this equation. We get the E is 2.329, and we can get the mass needed by using this equation, and the mass needed is 2,451.7625 kilograms. And for the reconstruction of transfer time, we first need to find the period of the transfer orbit, and the full transfer orbit, not just the mission trajectory. We get that the 486.13 days for the period of the transfer orbit, and now we know the t at theta of 180 because we assume the Mars is at theta 180 degree, and we found that we can find it by just dividing the period by 2, and we get it as 243.065 days. And we can also find the theta of Earth from theta 300 to theta 360. Sorry, we get it by subtracting the theta of 180 degree minus T2 minus T1. We can find T2 minus T1 by using this equation. The E1 is 180, and the E2 it can be found by using this equation. E2 is 312.22 degree. And also, after that, we know that the T2 minus T1 is 193.424 days. So we get the T needed from theta 300 degree to 360 degree is 49.64 days. So the T total for the mission is just this summed by this, and we get 292.71 days. And we actually found the actual mission duration is 208 days, so I think it's more accurate than other groups because but it's still not accurate because we assume the orbit is circular, the planet's orbit is circular, parking orbit is circular, and just to simplify our equation. Okay, I think that's it from our group. Thank you for watching and see you next time.